few of the things and kind of have a dialogue and discussion with Rupa on that matter. So thank you for introducing separability as well. The structure, oh, and actually very quickly, I want to mention, I saw on the list, Yuchin Zheng, I haven't seen him here today, but he is the person who is on the paper producing this ground state phase diagram we'll talk about later. And he was really, really helpful in preliminary discussions about this whole topic. He says somewhere, I haven't seen him. Thank you. It was a great chat. Yeah, hi, thank you, seriously. So the talk structure is fairly straightforward. I'm going to go through matrix product states. I know a lot of you here probably already know about them and how they work, but there is one specific thing I want to emphasize within them, and it's always good to review and go over those things anyway. Then I want to discuss the trick, how we construct the geometric measure, and then I want to show you some results. There's also some results later on that I can't talk about in detail, but that I want to show you the pictures of, because this work has generated some very pretty diagrams that I'm very well. And all of this, at least the stuff I'm going to cover in detail today, you can find in a paper of ours that went up on the archive about 11 months ago. So, oh, I need to click here. Yeah, cool. Okay. So first things first, matrix product states. For those of you who aren't too familiar with them, the main point that I'm trying to make here is that they are alternative representations of pure quantum states. Again, a divergence from Rupert's work. A conventional pure quantum state you can write like this in terms of a generic multi-dimensional tensor C. You have all the physical kind of microstates of your system indexed by these physical indices J, which for a spin system, your J's will be either spin up or spin down. For a anti-ferromagnetic Heisenberg ladder, they're going to be empty, 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 full, full, empty, full, full. And then you have a big tensor of weightings that is generally exponentially large. It grows with your Hilbert space. That's the thing that's stopping you from numerically simulating these systems. The matrix product state representation decomposes that multi-dimensional tensor into a bunch of local tensors that talk to each other. So you have your first A tensor, this is typically what I call the A tensors or A matrices, that describes kind of locally the state of your system and how it stitches together with the second site. And then that second one is describing locally the state of your system and then how it stitches together with the left and the right. And basically the size of these A matrices controls the fidelity of this representation. If you let the A matrices blow up to an arbitrarily large size, you can get a state that is an arbitrarily good representation of your original underlying pure quantum state. To see what kind of states matrix product states are really, really good at representing, it's worth digging into this guy. And this is where people who know about matrix product states are already going to be one slide ahead. No, I need to go here. Sorry. This bond dimension, as it's called in literature as well, chi, originates from how you decompose your big multidimensional tensor into these smaller local tensors. And conventionally, you use something called the singular value decomposition. It's just a matrix decomposition. So what you do is you take the first coefficient, this J1, you put it on the left, you take the rest of your coefficients, J2, J3, J4, J5, all the way up to Jn, and you move it over to the other side, fuse them all into one big index, and then you can decompose that thing that is now a matrix however you like. And the key thing here is this diagonal matrix S in the middle that stitches together your J1 and the rest of your fused indices J2, J3, J4, J5. This object is a diagonal matrix of singular values. And I had a thing here, I think we're a bit over, so in the interest of time, I'm not going to go into exactly how it relates, but these singular values are exactly the coefficients that you feed into the von Neumann entanglement entropy for the entropy of that subsystem. So if you want to calculate the entropy of the first site as half of your bipartition with the rest of the system, those are the coefficients that you use. So if we have a lot of varied values sort of in this diagonal matrix, they will sum to one, obviously, now because of this. But if you have a lot of different varied values in that matrix, that means you need to keep all of the information in U, and it means that chi needs to grow arbitrarily large. If a lot of them are zero, i.e. if you have less entanglement in your system, if rho 1 is not very well entangled with the rest of your system, or if across any given bipartition you don't have a lot of entanglement, then you can truncate these A matrices. You can throw away a bunch of terms in U, V, and implicitly in A, and you lose no information. It is a good compressed representation of your system. And those kind of states, states with very little, very short range entanglement that MPS are good at representing, are exactly those area law states that we heard about earlier. So that's an example of the kind of states that have good MPS representations. So the trick is that you should be able to quantify entanglement by how much an MPS fails. We're not trying to get a good representation. We are trying to restrict and constrain the size of those A matrices until the representation breaks down. And that should be a good way of quantifying entanglement in our system. I'm going to talk very quickly. In literature, you'll normally see matrix product states written like this as reparameterizations of your state in terms of the A matrices. To make the chi dependence explicit, I'm going to be using this notation on the right, just because it'll make some of the stuff we do later a bit clearer. So it looks like this. It looks like a geometric distance between our original state, psi, and its compressed matrix product state representation. And the key here is we're taking chi to be very, 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 very small. We are getting a bad representation of our state. For those, yeah, sorry. Yeah, of course.
Does it measure the geometric entanglement? Sorry, the multipartite entanglement.
Multipartite, no. Geometric, yes. We'll get onto it a bit later, but what you wind up with is two different partitionings of Hilbert space. So this is one trajectory you can go down. You can go down the K-separable way instead, and you get a different entanglement measure. But yes, that's exactly where we're headed.
And I guess there is some sort of optimization. I mean, this makes only sense if you try to make it as good as possible at a given kind.
Yes, exactly. That is a good point that I wanted to raise later. There should be, if you remember the conventional geometric entanglement, again, we'll talk about it later, a minimization here over your matrix product state. As it turns out, chucking away those singular values or just doing a kind of variational scheme which tries to determine this give you roughly similar results. It looks like the greedy approach, throwing away information, is about as good as a variation optimization. But yes, you tend to need a minimization here. We've tried it with both and haven't found substantial differences. It looks like a greedy approach is fine here.
But the original geometric entanglement measures the multipartite entanglement.
The original one measures the fully separable multipartite entanglement. So, for example, there are states that are separable. For example, I'll get onto it later. Something like the Majumdar-Bosch ground state, right, is separable, but it would register as having a very, very high geometric entanglement because it's not fully separable, which is where you run into some problems. So this measure is uniquely suited for dealing with systems which aren't separable or have a small amount of genuine multipartite entanglement, but still have very simple entanglement structures. Things like area law entangled structures that still have a little bit of long-range entanglement that you might want to account for. Yeah, please.
Just to be clear, here you need to project your approximation to psi onto psi, so you really need to know psi in order to quantify.
Yeah. If you're working with MPS, you need to make sure you've really converged on psi before you do any of this. Exactly.
So what if what you have is measurements of some physical system?
Then you can't do this. This at the moment is a numerical approach. We're thinking of ways to construct an analogy to this in experiment. So let's say you have a state psi. Can you, with a replica of your system and some gates, construct something that's related? But so far, no, it's a numerical approach. Okay. Nesting of Hilbert space. There you go. So you can conceive of this as a repartitioning of Hilbert space into a manifold of very, very low bond dimension MPS representations, and then higher and higher bond dimension ones that contain all of the lower ones within them. And what this looks like, this compression procedure, is you start out here, and you compress to a state that is the closest in this sense to your original state. But it's still a different state. You have thrown away and lost some information. Okay, we've talked a little bit about this. I'll move through this fairly quickly. The manifold contains the manifold of all MPS with lower chi. And as we talked about, the chi equals 1 states here are the product states. This second idea was where this work came from. I was looking for a really efficient way to calculate the geometric entanglement. And then we just let chi vary and saw what we got. So these properties of matrix product states lead to corresponding properties in our measure. Again, I'm not going to go over it in too much detail in this talk. I mostly just want to present the broad strokes, and if you want to talk about it, I'm very happy to chat throughout the week. And this is the comment on the geometric entanglement. So you can either partition your Hilbert space into different shells, nested shells, based on the matrix product state description, or based on separability. So you have fully separable states in the middle here, K separable, N separable, genuine, multipartite, entangled. And here you have chi equals 1, chi equals 2 for all the way up to omega, the full dimensionality of your space. And the fully separable, the chi equals 1 and the geometric entanglement are definitionally identical. They are all the same. That is where they meet and converge. And then you can go down these two different branches.
So, sorry.
No, please.
Sorry. Here, with geometric entanglement, you minimize over phi, right?
Yes.
Phi basically is just some parameter in product states.
Phi lets you hit every single state in your fully separable or K separable set.
What do you minimize over in this case?
Yeah, I probably should have written this to be explicit. Sorry, we explain it in the paper, but here it's a little bit kind of muddy. The minimization is implicit in constructing this matrix product state. As it turns out, a greedy approach is good. If it helps you, you can put minimization over MPS in front of here. And that's what's happening. It's just we've deferred it to a different place of notation. So I'm sorry about that. I should have been clearer. But again, I want to emphasize, even if you try to variationally optimize this, it's about as good as taking a matrix product state and throwing away all of the terms that are outside the bond dimension you're trying to hit. Those two are still pretty close to each other. So the greedy approach is about as good in this case, which is useful. It means you don't need to re-optimize your MPS to compute this. You should just to check, but you don't need to. Cool, okay. 3 classic systems, that's it. The AKLT model. This is a toy model with a known ground state. It is a Heisenberg interaction and then this AKLT term, JAKLT equals 1. This has a known ground state, which admits an exact representation as an MPS of bond dimension 2. So we know what we expect to see. At the bond dimension 2 generalization of this, it should be a perfect representation. And indeed, that's what we see. This is an example of a system which isn't separable, but does have, in some sense, limited entanglement that you should be able to capture. So the bond dimension 1 generalization, the geometric entanglement, doesn't see it at all as we scan across that AKLT point. And as expected, the bond dimension 2 generalization locates that point. And it gets stronger and stronger, the signature, as you go to larger system sizes. Another example, which is a little bit less constructed, here we knew what bond dimension we should take to actually find this thing, is the anisotropic Haldane model. So we have, again, spin 1 Heisenberg antiferromagnet here, and then an axial anisotropy in D, and a rhombic anisotropy in E. And if you vary all of these different parameters, you wind up with a phase diagram that has 7 distinct phases. And what was really nice here is that as we scanned this quantity across the phase diagram, different phases are revealed slowly as you scan up this bond dimension chi. You reveal more and more features about the underlying phase diagram. And the key thing here is this is something that tends to be quite difficult to do. Normally, when you're looking for phase transitions, at least in certain kinds of phase transition, you need to be careful about the quantity you use to actually look at it, because you need to pick something that's a good order parameter that can actually locate those phase boundaries. The nice thing about this is it's blind. We just shoved this thing in here because we thought it might work, and it did. And as we scanned up by more and more of the phase diagram was revealed. I'll mention scalings a little later, but we weren't able to find kind of any scalings or extract anything from this because it's a fidelity, it can't diverge. Bond dimension 1 doesn't find it because, again, nowhere across this whole phase diagram is this thing separable. And finally, many-body localization. This is another one which involves these non-separable but areal or entangled states. Where am I on time as well? Sorry, I'm a little bit. Stop them.
You started at 15 and now it's 28.
Okay, cool, thank you. 5. Sure, no worries. So this is another example where, so many-body localization, again, we've heard this before, whether or not it even exists in a certain sense. I'm going to use the word transition, but if you want to talk more about the transition, then I'm, again, happy to talk about that. But essentially, we're going to be using this as a toy model of many-body localization, which is a kind of a ergodicity breaking phenomenon, wherein this conventional, again, Heisenberg term would drive movement through the system. So if you make a local excitation or you make a local quench, that information spreads, gets erased, and gets non-locally distributed throughout the system. And then at recurrence times, it might come back, but generally, it's lost. Localizing fields, so strong random Z fields, stop that, or they limit and curtail that, especially within small systems. And for small systems, the critical value of disorder, the strength of these random fields is about 3.5. That's what we're looking for. So for very low disorder, where we expect information to be lost, mid-spectrum eigenstates is what we're looking at here. So mu is where in the spectrum you're sitting, 0 is ground state, 1 is highest excited, and all of these are very, very close to 0.5. So right in the middle of the spectrum, top row is bond dimension 1, bottom row is bond dimension 2. Both of them suck. They're both awful descriptions of mid-spectrum eigenstates in a space. Then as you scan through the ergodic to localized transition, again, 3.5 for systems this small is where you're expecting it. We can see that, brightness here is density of points. This is a lot of different random samples and a lot of different eigensets. Bond dimension 1 continues to be terrible. This just means, again, it's not fully separable. But bond dimension 2 starts to be a very decent representation, especially right here in the middle. And then as we go to an extreme side, we see bond dimension 2 almost across the board is a great representation. And even bond dimension 1 is starting to shift downwards. This is preempting the very, very strong disorder limit, where the first term becomes irrelevant, and you just have product states of local Z eigenstates. Those are your eigenstates as H goes to infinity. We decided to dig a little bit more into this. Again, this is just a kind of example. It's not really a toy model. We found some things, but it's a well-known and well-discussed model in literature. And if we average over each of these panels and we take the difference between the two, we want to try and quantify when one fails and when one succeeds. We end up with something that looks like this, which is probably as expected. We see really, really nice tending to zeros. Let's focus on the brown left-facing triangle here. That's the largest system size we went to with this one. On one side of the ergodic MBL transition, they're both equally bad representations, so it hits 0. On the other side, they're both equally good, so again, it tends to 0. And right here in the middle, we see some kind of scaling variance, as all of the systems, no matter what their size, converge on this point here, close to that 3.5, where for these small systems, this is expected to be. Again, here, we couldn't find anything like a scaling. Maybe we almost found something in the gradient, but again, it was a bit shaky, so we didn't really look into it too much. And the weird thing that I want to emphasize is that all of this work happened again about 10 or 11 months ago, and because it's fairly easy to construct, I've just sort of continued running stuff in the background. Now, whenever a project crops up, I'll compute this for a few sort of versions of the parameters in our model. And we started seeing some really, really interesting things with it. Unfortunately, they're not out yet, so I can't talk in too much detail, but we're starting to see some weird stuff, which is cool. If anyone wants to talk about this figure, by the way, I'm very happy to have a detailed chat about that. There's these weird sort of fringes that we see in the ground state phase diagram. It's like there's this length-dependent phase that's winding and unwinding entanglement. But anyway, the previous results were all toy models. We just wanted to make sure this thing worked. Now we're looking for more interesting stuff with it. But a big advantage is if you're already working with matrix product states, it's essentially a free lunch, provided you can show that variationally optimizing and truncating give roughly the same results. This is all just kind of running in the background as we do other stuff, which is pretty cozy. So there you go. That's my sales pitch. But yeah, thank you very much for listening. And are there any questions? Yes, please. Yeah, thank you. Sorry, there's 2 questions right next to each other. Yeah.
Yeah, thanks for a nice talk. Could you show again the AKLT?
Yeah, happily. Oh, right, sorry.
Yeah, so if I look at the right-hand panel, I was
Yeah.
trying to decide whether it was obvious what the infinite system size limit of that graph would be. Does it become singular, or is there some smooth sort of limit?
That, I don't know. The two are adiabatically connected, so there's a transition at one, but you can get from one to the other smoothly. So I really don't know. We have an infinite version of this. You have to be a bit more careful with the infinite version because overlaps aren't well defined. But I don't know. It's not something we've looked at. Yeah. Thank you. Sorry, you were next.
Question also relates to that plot. Does the system have an entanglement transition? That's what happens at j equals 1.
Yes, at that point specifically. Okay, yeah. You end up with change in the ground state degeneracy, but only at that point. Left and right, it is fourfold degenerate or not degenerate at all, depending on boundary conditions. But you end up with change in the ground state degeneracy at that point, but nowhere else. Nowhere else. Yeah. Sorry, at the back.
The same. You're showing the result of cycle 1, but what's happening to see any deep or see equally different?
Cycle to 3.
Yes.
Yeah, so it would be good to go back a few slides. I skimmed over this. They formed this hierarchy as a function of the properties of matrix product states. So what you see at chi equals 3 is essentially the same graph, but all of the lines are lowered. That's all. Yeah, exactly.
Which line? Chi equals 2?
Pardon? Sorry?
You see the transition of 3 to 4, chi equals 2 to j equals 1. The point you mentioned is that when chi equals 2 is sensitive to your transition, chi equals 1 is
exactly, yeah.
I'm asking chi equals 3 looks more like chi equals 2 or chi equals 1.
Chi equals 3 looks more like chi equals 2. It looks like chi equals 2, but all of the lines have dropped a bit. Yeah, exactly. In fact, what's kind of weird is we found a weird, I say weird too much as well, apparently, according to my office mate, but we found a scaling in the fidelity here. So I don't know, there's some self-similarity in these diagrams as you scan your one dimension as well, which is obvious when you think about it, but also only in hindsight. It's not something we expected to see, but having seen it, you'd expect it to sort of scale this way. But yeah, the best way to answer what you said is chi equals 6 here, looks like that. And if we go up to chi equals 8, it's essentially the same diagram, just a bit fainter across the board. So, sorry, there was one more or two. Thank you.
Just a question.
Yeah, sure.
So how about that we get a very accurate representation of the ground states
Yeah.
in MPS? So, I mean, if you say approach the critical point, you know,
incredibly important, as always.
Maybe you cannot approach it very closely, but does your method still work?
So the method is only as good as the underlying state psi. So there may be something in, these are some discussions that were ongoing 5 months ago, and then things fall apart. But we were talking about whether or not, if you try to make an MPS converge. Okay, so first of all, yes, you're correct. You need to have good convergence of that original state psi before you can do any of this. But let's say you can't. Let's say you're at a critical point, like you said. If you have a matrix product state of bond dimension 128 and 256, do they fail to converge at the same rate? Is something that I don't really know. And you could find something potentially interesting in the rate of how many coefficients you're throwing away, or something like that. There's something in there potentially that could be interesting. As you go towards the critical point, do both of these fail exactly the same speed? And that might give you an idea of criticality, but it's no, the way we do it, you need to know psi before you can do anything. So if you look closely at these diagrams, you'll see in those phase boundaries, there are quite a few little, you can't see it here because this one was actually quite nice. There are a few little dead spots where it didn't converge properly, and you just have to check the data.
Well, there's a relation maybe to finite entanglement scaling. Study how the correlation, like I say, depends on one dimension, but it doesn't have the scaling relation between these critical points.
Yes, yeah, there is.
Is there any relationship to the measurement? It's kind of a more fidelity point of view, similar concepts, sort of convergence. Is there any relation?
I don't know, not that I'm aware of, but it's an interesting one. Yeah, sorry.
Yeah. So I have a simple question. Like if the psi is the AKLT state and it's the chi dimension is exactly 2. So if I go from 2 to 3, then like it's that I just add a bunch of columns and rows of zeros to my matrix.
You start by adding a bunch of columns and rows. Yes, at that point, that's all you do. So all this is, if you went up to chi by 3, is your chi by 2 state padded with zeros and ones. Here and here, those zeros and ones would deviate. Sorry, not ones. Sorry, zeros. Those zeros would deviate because from this graph we can tell that an MPS of bond dimension 2 is not a good representation of the state here.
So, like even if the state is within the same phase, like the bond dimension changes. It's not.
Yeah, which is interesting. Again, you're looking for discontinuities, jumps, divergences, anywhere it goes to 0. But within a phase, it can still smoothly vary. It's just the structure of your entanglement hasn't changed. The ground state degeneracy hasn't. Cool. Yeah, please.
Yeah, follow-up question. I just want to ask what is the system size in your study? Is it infinite or finite size?
No, we stick to finite sizes. I only just figured out how to properly code and get infinite DMRG working myself. So this was all pre me learning how to do infinite. But yeah, this is all finite size stuff. Though I will mention your phase diagram is infinite. So this is using infinite DMRG. This is real. This is with 512, I think, spin 1 particles. So yeah. Sure.
Maybe this came up, but are you going to have a problem in 2D because there's there's area law entangled states that don't have a test?
Yeah, you're going to have a really big problem in 2D unless you can come up with a really good way of variationally optimizing. Yeah, you're going to have a problem with 2D.
Okay, maybe we should stop here.
Sure. Yes, thank you.
Right now until so 15. Well, we're running a bit late, so make that call. We should have 20 minutes.